Energy has quickly driven us to become an advanced civilization that builds sprawling cities and explores space using technology that our ancestors would have deemed impossible. Our evolution from an agrarian society to an international world, interconnected physically through incredible transportation capabilities, and digitally through vast data networks that power the internet, is only possible because of energy. But energy is dependent upon the critical minerals and metals that enable increasingly efficient energy production to carry the world forward. At this moment, we stand on the precipice of an energy revolution, as demand for dependable baseload power continues to increase, and we employ a wide range of energy sources, including wind, solar, and geothermal power, along with a renaissance in nuclear energy that is taking the whole planet by storm. The need for efficient and low-carbon energy is perhaps more vital than it has ever been in history, with the rise of artificial intelligence demanding more processing power, an emerging middle class in developing economies demanding a higher standard of living, and governments and citizens alike demanding cleaner air and less environmental impact as the Earth's population continues to expand. Today, we're going to take you on a journey through the periodic table to highlight the elements that are most important to modern energy generation. From copper, perhaps the most vital metal for electrification, to uranium, now needed more than ever, as policymakers get on board the nuclear train in search of a low-carbon future that previously seemed out of reach. Along the way, we'll discover how silver plays a vital role in solar energy, lithium's demand for electric vehicles and battery storage technology, and much more. This is the era of critical materials. Embrace the future and come along for the ride. In any discussion on energy, copper needs to be at the top of the list when it comes to critical materials. Although silver is technically the best metal at conducting electricity, copper's far more affordable cost, along with it being a close second in terms of conductivity, makes it the undisputed king of electrification. Copper's excellent electrical conductivity stems from its high concentration of free electrons. When a voltage is applied, these free electrons are pushed, allowing them to flow through the metal and generate an electric current. Materials with a greater density of free electrons can transmit current more efficiently than those with fewer electrons. In copper, the abundance of free electrons means they don't need to move rapidly, reducing the likelihood of collisions with atoms or impurities, which can hinder current flow. Additionally, copper plays a key role in enhancing the current rating, which indicates how much current a cable can safely handle without overheating. Copper wire is widely used in power generation, transmission, and distribution, as well as in telecommunications, electronic circuits, and various electrical devices. Beyond its conductivity, copper wire is prized for its high tensile strength, ductility, resistance to deformation and corrosion, low thermal expansion, high thermal conductivity, ease of soldering, malleability, and ease of installation. If the world had unlimited access to this vital resource, then we could grow our electrification capacity to match the ever-rising demand. But alas, the current supply dynamics for copper are far from favorable. In fact, S&P Global released a report on copper where they stated, unless massive new supply comes online in a timely way, the goal of net zero emissions by 2050 will be short-circuited and remain out of reach. This report is just one of many that have echoed similar sentiments. We need more copper, and we need it as soon as possible. The problem with that? Even if we set net zero emissions goals aside, there's currently nowhere near the amount of producing copper mines needed to meet demand from a rapidly rising middle class in emerging economies such as India, China, Brazil, and many others. In India, a country with a famously arid and hot climate, where in some areas, Heat waves of up to 122 degrees Fahrenheit put lives at risk. Only approximately 8% of households own an air conditioner. The International Energy Agency, also known as the IEA, expects this number to grow rapidly, not only in India, but internationally, making air conditioners one of the top drivers of electricity demand worldwide. Because copper is an excellent conductor of heat, it is used widely in air conditioning systems, on top of its use in the wiring that powers AC units. Pivoting to China, we see a lot of doom and gloom headlines about their economy. But the fact is, they are making massive investments in their electricity grid, and at the moment, the government-run State Grid Corporation is the world's single largest buyer of copper. When it comes to Brazil, recent research by the Energy Research Company estimates that electricity demand in the country is set to grow by 3.4% per year for the next decade out to 2034. Brazil is also planning to expand its renewable energy capacity in the form of wind and solar, two technologies that require copper to be operable. These three countries are just part of a massive and persistent trend of increasing demand for electricity. The International Energy Agency has projected that growth in demand for electricity worldwide in 2024 and 2025 alone is among the highest it's been in the past 2 decades. And as AI data centers become more commonplace, this demand is only expected to accelerate. Speaking of AI, did you know that cumulative copper demand for data centers to 2030 is forecasted at 5 million metric tons, equivalent to 3% of 2030's global demand? Quite a substantial figure, and it underlines another necessity for AI, the need for reliable, clean baseload power generation, which is where nuclear energy and uranium come into the mix. Here's an interesting thought. There does not exist a wealthy country with low energy consumption. The challenge in our world today, as the global population expands and more people aspire to reach for a greater quality of life, is in producing more reliable, low-carbon baseload electricity. Enter nuclear energy and uranium. Once maligned by officials and policymakers who hadn't done their research, the truth is now coming to light on nuclear, revealing it to be one of the safest, cleanest, and most reliable forms of energy in existence. As a result, countries are scrambling to construct new nuclear reactors, along with extending the life of reactors previously set to be decommissioned and restarting reactors that have already been decommissioned. And all of this is going to require a lot of fuel in the form of uranium. Adding to this, small modular reactors, or SMRs, which provide all the benefits of full-on nuclear plants in a much more convenient size, are being proposed and developed en masse, with companies like Rolls-Royce, General Electric, and Hitachi working on models right now. As AI data centers proliferate around the world, the electricity required to reliably run them is projected to be 7 times greater than traditional data centers. As a result, mega corporations such as Microsoft and Amazon have placed their bets on nuclear energy in a big way, with Microsoft signing a deal to restart part of the once vilified 3 Mile Island nuclear plant, and Amazon announcing plans to invest more than $500 million to develop SMRs, in addition to their purchase in 2024 of a nuclear-powered data center in Pennsylvania. These developments are just the tip of the iceberg, as there are currently around 67 nuclear reactors under construction worldwide, with a further 87 in the planning phase on top of the approximately 438 reactors currently operating. As for uranium, it is the lifeblood of the nuclear industry, currently being the primary fuel for large-scale commercial nuclear power generation. The vast majority of nuclear reactors, known as pressurized water reactors, require enriched uranium as fuel. The road to uranium enrichment is fairly complex and requires several steps. Firstly, after the raw uranium ore is extracted through mining, it must be refined into uranium concentrate at a mill. This concentrated uranium is referred to as yellow cake, and around 1 to 4 pounds of yellow cake can typically be extracted from 1 ton of ore. Next, the yellow cake must be converted into uranium hexafluoride gas, also known as UF6, at a converter facility. After being converted to UF6, the uranium needs to be enriched. This is because 3 forms of isotopes occur naturally in uranium: U-234, U-235, and U-238. The vast majority of reactors require uranium with a higher U-235 concentration, and so through enrichment, the isotopes are separated to produce a UF6 with a 3 to 5% concentration of U-235, and the material is rendered back into a solid form. Finally, the enriched UF6 is heated back into a gaseous form and chemically processed to produce uranium dioxide powder, also known as UO2. This powder is compressed and formed into ceramic pellets, which are stacked and sealed into fuel rods that are then bundled together to create a fuel assembly, and they are now ready to be used in nuclear reactors to produce an extremely efficient form of energy. Although there is some research being done into alternatives for uranium as nuclear fuel, such as thorium, commercial scale deployment of such alternatives are likely decades away, if not further, as all current reactors are built to use uranium. The World Nuclear Association has projected that demand for uranium in nuclear reactors will grow by 24% by 2030 and rise 92% by 2040, largely driven by the nuclear renaissance currently underway, as nations seek to embrace low-carbon, baseload electricity and reduce their dependence on fossil fuels. Geopolitical uncertainty also plays a role here, as we have already seen energy prices soar across Europe due to natural gas supplies being cut off from Russia, leading governments to want to take their energy destiny into their own hands. At the moment, the amount of uranium being produced globally is nowhere near meeting growing demand. And in 2023 alone, a whopping 39% of the world's uranium was produced in Kazakhstan, a country that continues to align itself with Russia and China as the world bifurcates into West and East amid heightening resource export restrictions to unfriendly nations. Now that we've covered perhaps the 2 most important critical materials to electrification and energy generation, let's take a look at some others that stand out as essential ingredients in powering our planet. One vital piece of the energy puzzle we haven't yet covered is the rise of energy storage, in the form of batteries, both for electric vehicles and energy grids. The main mineral at the heart of this is lithium, and indeed, we have already seen demand for lithium soar by 193% from 2019 to 2023, largely driven by the EV revolution, with many analysts predicting a continued rise in the years ahead. Nickel, manganese, cobalt, and graphite are all elements that will also play a big role in battery storage technology, with a focus on EVs. And with nearly 14 million electric vehicles sold in 2023, approximately 4 times the sales from only 3 years prior, and an estimated 16.7 million projected to be sold in 2024, this is a trend that looks like it is here to stay for the foreseeable future. And that means increased demand for all battery metals. We mentioned earlier that silver is actually the greatest conductor of electricity and continues to be one of the most used commodities on the planet, essential for everything from smartphones and computers to aerospace technology and so much more. But its growing use in photovoltaic solar panels may be the most intriguing aspect of the metal's supply-demand dynamics. Silver demand from solar panels has already risen rapidly from 2014 to 2023, going from around 50 million to nearly 200 million ounces per year. And this too is expected to grow as solar energy is embraced around the world. Combine this with silver's 5,000-year history as money, and you have one of the most unique hybrid metals that is both a massively demanded industrial commodity and a store of value in uncertain economic times. The International Energy Agency forecasts that electricity demand worldwide will grow by 169% by 2050 due to a multitude of catalysts. Massive increases in energy consumption coming from emerging economies in the East, driven by urbanization and industrialization, along with citizens of those countries seeking to upgrade their quality of living through air conditioning, refrigeration, electronic devices, and more, is set to play a key role in growing electricity demand. In the West, the AI revolution is well underway, and AI data centers are going to require levels of energy far and above what was forecasted before this technology emerged. Reshoring of resource production and manufacturing due to rising geopolitical tensions is also a big driver when it comes to energy demand. And as nations start to bring industries home that were previously outsourced overseas, the energy inputs required to ramp up production will need to be met, one way or another. Finally, the energy transition isn't going anywhere. With more and more countries pledging to reduce carbon emissions and invest in green forms of energy generation, such as solar, wind, hydro, and geothermal. Battery storage technology is also evolving, and electric vehicles continue to be one of the main trends moving many of the critical materials we've covered to the forefront of the global energy discussion. At the end of the day, one thing is certain. The world will need more energy, not less, to advance to a brighter future. And the building blocks for that future are the critical materials that drive electrification, energy generation, and energy storage into the next exciting phase of our ever-expanding civilization.